Hello, everyone. In the previous lesson, we studied the three different operating modes of the neutral point in power systems. We separately analyzed the operating characteristics of these three modes, particularly the impact of voltage and current changes on the power system, as well as their respective advantages and disadvantages. We understood how different neutral point operating modes in power systems affect power supply, reliability, safety, stability, economic efficiency, etc. Now, let us study the content of this lesson together. A comparison of the three different neutral point operating modes and their applicable ranges. Through this lesson, you are required to master the application scope of various neutral point operating modes in power systems. Develop the ability to compare and analyze various neutral point operating modes in power systems, cultivate a good awareness of safe electricity use, and improve analytical and judgment skills. The key point of this lesson is the comparison and application scope of various neutral point operating modes in power systems. The difficult point is the comparison of various neutral point operating modes in power systems. How do we compare the different neutral point grounding operating modes? What aspects need to be compared? The three neutral point operating modes exhibit different advantages and disadvantages in operation. Among them, issues such as power supply reliability, overvoltage and insulation level, sensitivity of protection relay operation, interference with communication, and system stability are all highly relevant to power system operation. Below, we will analyze and compare these aspects one by one. First, let's look at power supply reliability. From the previous lesson, we know that in small current grounding systems, when a single-phase ground fault occurs, the system can continue to operate normally for 2 hours. Whereas in large current grounding systems, when a single-phase ground fault occurs, the current instantly increases to the short-circuit current level, and the protection relay device immediately trips, cutting off the faulty line and causing a power outage for users. Thus, power supply reliability is lower than that of small current grounding systems. In arc suppression coil grounding systems, due to inductive compensation, overvoltage and arcing phenomena in the system are suppressed and weakened, so they have the highest power supply reliability, followed by neutral ungrounded systems. Next, let's look at overvoltage and insulation level. In small current grounding systems, when a single-phase fault occurs, the voltage of the non-faulted phase rises to the line voltage, increasing by a factor of √3, and the faulted phase may experience overvoltage, forming an arc. At this time, the insulation level must be designed considering the line voltage so that the system can withstand the highest elevated voltage without breakdown, etc. In large current grounding systems, when a ground fault occurs, the voltage of the grounded phase drops to 0, while the voltage of the non-grounded phases remains unchanged, still at the phase voltage. Its insulation level must be designed considering the phase voltage. The insulation level of large current grounding systems can be about 20% lower than that of small current grounding systems. When a ground fault occurs, the protection device trips to remove the faulty line, avoiding sustained arcing at the grounding point and reducing overvoltage. Therefore, large current grounding systems have lower overvoltage, lower insulation level requirements, and higher economic efficiency. Next, let's look at the requirements for protection relay devices. This is related to the potential hazards when a fault occurs. In large current grounding systems, when a ground fault occurs, the current instantly increases to the short-circuit current value. The system's protection relay device needs to trip immediately to cut off the faulty line. In small current grounding systems, when a ground fault occurs, the system can still continue to operate normally for at least 2 hours. If the fault is not eliminated, the protection relay device can act with some delay to cut off the faulty line. Therefore, large current grounding systems have higher requirements for protection relay devices and require higher action sensitivity. Next, let's look at the interference with communication. The greater the current, the greater the magnetic field, and the greater the interference with communication. In large current grounding systems, when a ground fault occurs, a short-circuit current appears, causing significant interference to nearby communication lines. The induced voltage may endanger personnel safety and cause misoperation of signal devices. Therefore, a certain distance must be maintained between power lines and communication lines. In small current grounding systems, when a ground fault occurs, the current generated is relatively small, mainly producing electrostatic induction, which can be limited by relatively simple methods. Here we must emphasize that the interference caused by single-phase grounding on communication is absolutely not negligible and, in some cases, can even be a decisive factor in selecting the neutral point grounding method. From the above comparison, we can see that, from the perspective of power supply reliability, small current grounding systems should be prioritized. From the perspective of overvoltage and insulation level, large current grounding systems should be prioritized. From the perspective of protection relay device action sensitivity, large current grounding systems should be prioritized. Then, from the perspective of communication interference, which type should we choose? Small current grounding systems in actual production processes. What are the specific application ranges of the three neutral point operating modes? Different voltage levels have different requirements for system operations, safety, stability, power supply, reliability, insulation, cost, etc. What are the specific application ranges? Let us take a look together. For 110 kV and above, we need to adopt a neutral point directly grounded system for 20 to 60 kV. When the current is less than 10A, adopt a neutral point ungrounded system. When the current is greater than 10A, adopt a neutral point grounded via arc suppression coil system for 10 kV. When the current is less than 20A, adopt a neutral point ungrounded system. When the current is greater than 20A, adopt a neutral point grounded via arc suppression coil system for 3 to 6 kV. When the current is less than 30A, adopt a neutral point ungrounded system. When the current is greater than 30A, adopt a neutral point grounded via arc suppression coil system. For 1000B and below, adopt a neutral point directly grounded system. From the above, we can see that the higher the voltage level, the wider the impact, the higher the requirements for protection relay devices. And the higher the economic requirements, the lower the voltage level, the relatively lower the requirements for system stability. In this lesson, we compared the three neutral point operating modes in power systems in terms of power supply, reliability, overvoltage and insulation protection relay, device action, sensitivity, communication interference, and other aspects. We also introduced the application ranges of the three operating modes. We hope that students can apply the content of this lesson to practical work cases. Please use your spare time to look up information and find some cases related to the three neutral point operating modes in power plants and substations. That is all for this lesson. Thank you for listening.